I will give you a quick update on the interface of FreeFEM to PETSc, SLEPc, and HPDDM. There are not that many new stuffs with respect to last year, but anyway, there are some new faces, and I'm covering the basics, so it's never a bad idea to read oneself.
Sorry, we cannot see your slides.
You cannot see my slide because I'm not sharing. Is it any better?
Yeah, that's fine now. Yeah, we can hear you and big slides. Thank you.
About that. So if you want to follow along, or if you have, if you want to get some details. Get the slides online, and so the presentation is quite straightforward. I will just give a very quick introduction, and then I will jump into the details. So when it comes to FreeFEM, I think most of you are aware of the fact that so FreeFEM is basically a domain-specific language for finite elements. And so we have access to various tools for performing finite element analysis. So a mesh structure, which can be either 1D, 2D, 3D, surface mesh, and whatnot. Then using these meshes, we can define finite element spaces using a variety of finite elements. So Lagrange, Verdier-Thomas, Brézy-Douglas-Marini, whatever. And then using both the combination of the finite element space and the mesh structure, we can perform both linear and bilinear assemblies. And at the end, what we are interested in is most often solve linear systems. And so basically a set of algebraic operations like solving linear systems, doing vector summation, matrix summation, and whatnot. So when it comes to PETSc, so PETSc is a library which is called the portable, which stands for the Portable Extensible Toolkit for Scientific Computing. And so you can think of it as an algebraic backend that can be used in conjunction with FreeFEM. Okay, so if you are a FreeFEM user, you are free not to use PETSc, but you can also leverage all the tools that are delivered by PETSc. And so even if you don't use PETSc inside your own code, you can use it to install a lot of packages. As Frédéric just mentioned, the interconnection between various packages is quite painful to deal with. The compilation is always a difficult process. And so if you want, we can actually install and compile a lot of packages automatically for you, either directly inside FreeFEM or through PETSc. Okay? And so in PETSc, in FreeFEM, if you type make PETSc SLEPc, this will basically install for you a lot of packages, including PETSc. And so the various packages that you get will be MPI-PH, so which is an implementation of the message passing interface standard, which can be used for performing parallel computing. If you already have MPI on your machine, PETSc automatically detects that and does not install another MPI implementation. If you don't have SLEPc, we automatically install it for you. Again, if it's already on your system, PETSc detects that and does not install it. We install Bison, we install OpenBLAST, but again, if you have something like DMKL or another vendor library, we don't install it. If you have Fortran available, we install MUMPS, which is a linear system, a software for solving linear systems of equation. If you don't have Fortran on your machine, we install instead SuperLU distributed. We also install SuperLU, which is the same as SuperLU distributed, but for plain sequential computation. We install ShootSparse, which is the default linear solver in FreeFEM. We install Hyper, which is a set of solver for algebraic multigrid. We install Metis and ParMetis, which are graph partitioner. We install Scotch and PTScotch, which is another set of graph partitioner, mesh partitioner. We install TEDGen, which is a mesher. Then we install SLEPc, which is the scalable library for eigenvalue problem computation. Sorry. If Fortran is available inside SLEPc, we also install RPAC. If you have support for shared libraries on your machine, so basically all machines except Windows, we install HPDDM. And then we wrap this up with MMG and ParamMG, which are remesher, sorry, and HTool, which is a library for hierarchical matrices. So again, just as for FreeFEM, PETSc is also tested on a wide variety of architectures, and so we are making sure that the combination of both FreeFEM and PETSc is interoperable on various architectures, and so we have tested the make PETSc SLEPc step on Windows, Linux, Apple, A64FX, and so on and so on. So of course, this is just a small list of packages that is both used by FreeFEM and by PETSc. So I think if I'm not wrong, in FreeFEM, we have the ability of downloading the same list of packages plus a couple of others like IPOpt and LOpt, that was mentioned this morning by Frédéric. So I think overall, if you look at the file third-party get all, we have about, I want to say, 20 packages. Okay. If you look at the same thing in PETSc, there are about, I think, 60 packages. So there are many, many more that are not used by FreeFEM. But for example, we could think of adding other packages like HDF5, GSL, Boost, Zlib. So all those are installed either by FreeFEM or by PETSc. And for the moment, when we do make PETSc SLEPc, we don't install them via PETSc, but we install them later on via FreeFEM. So if you need some packages, for example, not so long ago, someone asked for using GPUs with FreeFEM. And so, for example, we don't download any GPU-related solvers, but we could add, for example, a StreamPack, which is a distributed linear solver which uses GPUs. We could use download Magma, which is a dense library for computation on GPUs and stuff like that. So keep in mind that all of this works both in sequential or parallel. But what I mean when I mean sequential here, I mean using FreeFEM++ MPI, but with a single process. Okay? So for the moment, there is no interface with PETSc through the plain FreeFEM binary, FreeFEM++ binary. We could add another package, which would be a PETSc built without MPI wrappers. But as Frédéric mentioned this morning, we already have PETSc complex. And so if we wanted the same for just plain FreeFEM++, we would have to compile PETSc sequential, PETSc complex sequential, PETSc parallel, and PETSc parallel complex. So it's getting a little bit tricky. And so for the moment, you must use FreeFEM++ MPI, but with a single process, it's running just fine. So if you are not very familiar with PETSc, I will try to give you a quick introduction and an overview of the library. And so when you think about PETSc, when you think about FreeFEM, as I mentioned in the beginning, it's the approach is quite monolithic in the sense that you have your domain-specific language with your meshes, your variational formulation in your finite element space. And so the design of PETSc is a little bit more hierarchical in the sense that there is basically a set of classes that are sitting one on top of the other. And so if we do, for example, a top-down overview of the library, at the highest level, it's possible to use time steppers. So if you want to use fancy method like implicit, explicit method, high-order Runge-Kutta method, everything is available in PETSc and interfaced in FreeFEM. You can also have optimization solver like interior point method, PDE constraint method. Some of them are available in FreeFEM, but not everything is linked currently. There are some. Then below that sits the nonlinear solvers. So of course, you can write down your own Newton method by hand in FreeFEM. Actually, it's quite nice if you want to learn about solving nonlinear problems. But if you are tired of writing Newton loop by hand for 20 years, you can also use nonlinear solver directly from PETSc. And so again, you can do Newton method with line search, Newton method with trust region, BFGS, and whatnot. And so in the end, solving nonlinear systems of equations boils down to solving linear systems of equation. And so at the lower level, you have what they call KSP, so Krylov subspace solver, like conjugate gradient, GMRS, Krylov method for those who know what that is. And so when you need to solve a system of equation with an iterative method, you most often need to use a preconditioner. I will focus slightly more on this part later on. So what's important to keep in mind is that I'm mostly focused on the left-hand side of the figure. You can see here that we have something which is called domain management in PETSc. And so it's what's used in PETSc, for example, to deal with a particle method, to deal with oak trees, so for structured forests, and so on. And so currently in FreeFEM, there is very little interface between the domain management and FreeFEM. We have just a small interface with respect to DMPlex. And so DMPlex in PETSc are a way to deal with unstructured meshes. And it's the only domain management type which is interfaced. Okay, so if you are interested in, for example, particle method or regular grids, so DM, DA, Cartesian grid in FreeFEM, please let us know and we'll see what we can do. Still, it's nice to have the DMPlex format because, for example, it means that you can load GMSH binary format version 4. Whereas if you stick to the GMSH plugin in FreeFEM, I think we are limited currently to the version 2 in binary or ASCII. If you have like a qubit mesh format, a fluent mesh format, there is a lot of different mesh formats that are handled by DMPlex, which are not necessarily handled natively via FreeFEM. Okay. So then the question remains, how do we make the link between FreeFEM and PETSc? And so for this, I will mostly focus on the matrix part. And so I'm guessing that most of you are familiar of the type matrix, which is the type used to store a bilinear form or a matrix in FreeFEM. And so in PETSc, there is another type, which is called mat. And so it's the only difference between a PETSc matrix and a FreeFEM matrix. If you have a FreeFEM matrix, it's quite easy to transfer or to transform your FreeFEM matrix into a PETSc matrix using something which is probably familiar to those of you who are familiar with C++. We basically have a constructor which builds a matrix B using the FreeFEM matrix A. And so then you are free to use all the PETSc machinery with your new operator B. So what's important to keep in mind is that once you have your PETSc matrix, we try to make it possible to perform all the algebraic operation that you were able to perform with your FreeFEM matrix, the same with the PETSc matrix. Okay, so ideally, we want you to change as little as possible your code to try out PETSc. And so in practice, in sequential with a single process, we aim, the goal is for you to just change your matrix to a mat, and then hopefully everything should work out. So you can perform matrix vector multiplication, you can solve systems of linear equations, you can do Hermitian matrix product, you can solve Hermitian transpose system, you can do whatever you want. So once you are a little bit more acquainted with the PETSc tools, hopefully you can then parameterize your solver the way you want. And so this can be done through a set of parameters using S-params. And so again, this is somehow similar to what you can do with a plain matrix. So what's important to keep in mind also is that FreeFEM is a very nice way to try to prototype your algorithm, your solver parameters and whatnot. And so the idea is then, if you have some specialized software for doing your own discretization, or if you want to implement something more efficiently on your own outside of FreeFEM, you should be able to basically copy-paste the option that you use for your PETSc options into your own code, your commercial software, let's say, if it's using PETSc, it's just a matter of copy pasting. So a little difference with respect to matrices in FreeFEM when it comes to the matrix from PETSc is that we have a single exposed type, which is mat. And so if you are familiar with the different type of matrices in FreeFEM, there are multiple types. For example, there is matrix for sparse matrix. And for example, there is also H matrix for matrices stemming from the boundary element methods when you discretize BEM kernel. So in PETSc, it's a little bit like C++. You have a single exposed type, which is mat. And so inside this mat in FreeFEM, you are free to assemble a FEM operator, a BEM operator, a dense operator. There is no changes of type with respect to the main type mat. But under the hood, of course, there is a dispatch between different matrix type. So for example, when we assemble a varef, a finite element varef, we use a mat aij, so this is a sparse matrix, just as matrix in FreeFEM. If we assemble a varef which is declared symmetric, so when you assemble a varef, you can put a parameter which is sim. Then we assemble a symmetric aij matrix, so SDAJ. When we assemble a varef coming from a BEM variational formulation, we assemble this using a... Ah, j'ai un problème de... Non, c'est juste, j'entends pas si les gens me parlent, mais... Si. Ah bon? Oui, non, c'est moi si je veux les entendre, mais je pense que certains d'entre vous... Bah, je vais mettre... Everyone can hear me okay on Zoom, right?
Yeah, we do.
Okay, thank you.
Yeah.
C'est juste que moi j'ai coupé le son, je crois, mais bon, je... So H2, yes, it's used for BEM kernels for doing compression. Then we can use other types which are slightly more involved. I will show examples afterward. So for example, matnest. Matnest is a way to define block matrices, just as in FreeFEM. Matshell is a way to define operators that are just defined by the product of a matrix on a vector. So for example, unassembled matrices. If you don't have your matrix which is assembled, but just know its action on a vector. Matdense is for storing dense matrices. Composite matrix, it's not the same as composite FE space in FreeFEM. This is a little bit misleading, just thought about that. So in PETSc, a mat composite is basically a product or a sum of matrices that you don't want to assemble. So for example, if you want to compute AB times a vector U, but you don't want to assemble the product AB. So you want PETSc to first compute B times U and then A times U. So this is a mat composite. MAT-IS, which is used for unassembled operators. So this is a little bit technical. I won't go into the detail. And MAT transpose, it's when you want to compute the action of a transpose of a matrix without assembling the actual transpose. Okay, so again, I've shown you some nice tools, but then the question remains how to make the code go faster. And so, as Frederic mentioned, for the moment, we have no shared memory parallelism in FreeFEM, so we don't use spread, but we use quite extensively the distributed memory paradigm through MPI, so the message passing interface. So I will show you an example. Okay, so for the moment, it's not quite fully transparent to the user. So there is one way to make it transparent for now. It's slightly suboptimal. We are in the process of making this a little bit more efficient. But if you want something which is the most efficient, let's say, you need to add some lightweight macros for performing the workload distribution. So what is the workload distribution for MPI in the context of finite elements? Well, you have to keep in mind 3 points. The first one is that basically you will have different processes talking one with the other. And so each process will be in charge of a local address space, or a local mesh, a local matrix, and so on. we want to try to distribute the workloads such that multiple domains will have the lowest amount of communication possible. And so hopefully one day we will be able also to couple this with shared memory parallelism. But in practice, in theory, it's purely orthogonal. So we could mix OpenMP with MPI, but we don't do it currently. So just to give you an example, if you think about a mesh, for example, and you do distributed memory parallelism on such a mesh, 99.99% of finite element code will basically take this mesh and then decompose it into smaller pieces, so subdomains. And so the idea is to have something which is evenly distributed and where there is the least amount of communication on the interface among what we call subdomains, but you can call that submesh or whatever you want. Okay, so once you have that, you can think, okay, everything is fine. I can do everything in parallel, and everything will run perfectly fast, and so on. I can just use as many subdomains as I want. Because basically you can perform the assemblies in parallel. But of course, it's not the end of the story. There are still many algorithms that are very challenging to perform in a distributed memory context. For example, computing the distance to a level set. So if you think about a level set which is distributed among multiple processes, and you want to compute the distance to this level set, it's not trivial to do in a distributed fashion. Unstructured additive mesh refinement is also a very challenging topic. And then remains, of course, the question of the nonlinear solvers and the linear solvers. So I will show you yet another example. For example, FreeFEM is known to perform interpolation very easily and quite efficiently, at least in sequential. So in FreeFEM, you can go from one mesh to another, one finite element space to another. But then when you think about coupling this with distributed memory parallelism, for example, you can think of having two meshes on the left-hand side and on the right-hand side. Both of the meshes are distributed among 4 MPI processes. So you can see that one mesh is not included in the other. And so then how can we interpolate a solution on the domain, on the square domain to the domain with a hole inside? It's very challenging because, for example, you can see that the green green subdomain here, for example, let's say it's subdomain number 1, then lives here, and so doing the interpolation in sequential is somehow straightforward. But then doing this interpolation in a distributed memory context is much more challenging because you need to exchange with the proper processes which are in charge of the proper part of the image domain, and so there are challenges, let's say. Still, we provide the tools for performing those kind of operations. And so most of these are available in a file which is called macro_ddm.edp. And so, for example, we provide tools to save a distributed mesh such that you can then load it if you want to do, for example, snapshots and restart your computation after a while. We provide tools to automatically distribute a mesh among multiple processes. We provide tools to create a PETSc matrices, and we provide tools to do interpolation of vector or create an interpolation matrix between two meshes that are divided, that are not necessarily the same. So basically, a tool for performing the interpolation between the left-hand side mesh and the right-hand side mesh with a different distribution. So there are many available examples. As Frédéric mentioned, you can look the changelog.md to track for changes. And so there is a tutorial available specifically for the parallel computing stuff on the web. Okay, so now I will focus on some advanced functionalities. And so one first step kind of operation are, for example, eigenvalue problem and non-standard eigensolvers. So in FreeFEM, there are two ways to solve linear eigenvalue problem, either through RPAC or through SLEPc. Both should give you approximately the same performance when running in sequential. RPAC is quite difficult to parallelize, but you can do some trick to make it parallel. SLEPc, on the other hand, is parallel by default, but the basic algorithm is the same in both cases. Then if you switch to, let's say, more advanced problem like nonlinear eigenvalue problem, polynomial eigenvalue problem, and singular value decomposition, this is only available through SLEPc. So again, I want to emphasize that the structure of the PETSc matrices are very like the syntax for plain FreeFEM matrix. And so, for example, we can use this notation, which defines an array of n PETSc mat. So I will try to show you an example. So of course, we need to add the additional plugin PETSc, but then if you have something like TAC, you can do matrix int TAC, and then you can do also mat int. So it does nothing, but it runs, and so the syntax is roughly the same. And so this is useful, for example, for polynomial eigenvalue problems where you need to define an array of matrices for the problem to solve. We also made the use of shells as easy as possible. So in PETSc Linguo, a shell again is nothing else than the action of an operator on a vector. And so we can define a mat shell in FreeFEM. So for a mat shell, you need to provide the action of the matrix on the vector, so the product of A times U. And you can also define what is called a PC shell, so the action of a preconditioner on a vector. And so, for example, if we look at the Austin equation, so in computational fluid dynamics, we have a block structure that looks like this, where F will be the velocity block and C the pressure block. And so the structure of the operator is just the same as in plain FreeFEM. So in FreeFEM, you can do matrix A equal your block operator, and you can do exactly the same in PETSc mat. So I will try to show you an example. I won't do the full Austin problem, but I will just use a toy problem. So for example, matrix diag equal I n. Then I do the B, I will use something of dimension. So same number of rows and let's say only 2 columns. And so then you can do matrix block equal diag B transpose, let's say 0. And so hopefully this will work. You can do exactly the same, but again, I have to switch to a matrix from a matrix to a mat. So mat diag, let's say, and then I mat block equal diag, diag B transpose. Okay, just I want to make sure that I'm not doing something wrong. So I will do a C out of block. And then I will do a mat view of block.
I think put something in B. So make B equal 1.
Sure.
B equal 2.
B 0, 0 equal 1. B 1, 1 equal 1. And B equal 0. Sorry, not mat view, object view. Object view. Okay. So we have the diagonal part, and then we have the 0. Ça démarre à 1.
Yeah, no, the print starts the numbering by 1.
No, here it's 0.
Yeah. You know?
0.
Yeah.
Wait.
No, it's not BCSR because it's a full
Sorry.
matrices.
Okay, now it starts properly at 1. Okay, so we have
Yeah.
but was there a bug before?
It's not print, it's not the same print.
0.5 should be 1.
Yeah.
I don't know why it's 0.
Yeah,
Anyway,
because it's a full matrices, so they put the coefficient of the full matrices in the sparse. They don't remove the 0 coefficient.
right, but here I'm putting 1, so the matrix should be.
So I put 10 rather than 9. Put 10 rather to put 0 in line 9 or 12.
No, but here it's fine. This one is working. Anyway, it's no big deal. Everything works in FreeFEM, don't worry.
In your block matrix, you can put matrix of real int arrays, but you also put matrices.
Yes, sure.
So you can define the SLEPc matrix using block matrices from any type.
Exactly. So for example, good question. So as Frederick mentioned, this is a dense matrix. So here it's quite wasteful because we have a lot of 0. And so I think in FreeFEM, if I'm not wrong, we have something
B equal B
to convert from dense to sparse. And so then we can, for example, we can put here, we can put a sparse matrix instead of a dense matrix. And then we can do the same here. Math, I'm not very sure I like BB. Which is a conversion of the FreeFEM matrix, and then I can put tuck. Okay, so I won't check that everything works, but so what's important in FreeFEM, this syntax is very powerful because you can very couple a lot of things. For example, if some of you do fluid structure interaction, you are probably ending up writing block operators like that. And we tried the best we could to make the syntax the same for PETSc matrices. And so you can couple, you can put as blocks a PETSc matrix. I don't think we can put a FreeFEM matrix, so I will try this. BSP. I don't think this will work. Unsupport type in submatrix. We can, inside the PETSc block matrix, we can put a matrix. Sorry, a PETSc matrix, a FreeFEM dense matrix. We can put a transpose matrix. We can put a constant. Rectangle, yes. Yeah, sure. So again, we try to mimic as much as possible the FreeFEM syntax so that everything is interoperable and you can switch back and forth. Okay.
So why when you write object view of a block,
yes,
wouldn't it be possible to have cout of block?
I will add that.
Okay.
So as Frederick mentioned, you need to ask us what you want. Cout of block. So we could overload the operator.
Yeah, but be careful because it's quite difficult because you don't know
if it's a file.
The type of the block.
Yes.
So because when you say matrix equal, you know that you build a matrix or you build a man. When you may say out, you have to take everything.
Yes.
So
it can be.
It could be tricky.
I will try if it's possible. Yes.
Is it possible also to make block of sciences 3x3 or 4x4? Or
sure.
Because I remember that in the past.
No, it's you can. I think it's arbitrary order. So if I do this. Wait.
No,
One.
1, 0.
So just for good measure. The same applies to both matrix and math. The block notation is quite flexible, and so it's also possible to add new types. So for example, what's something which may break in FreeFEM? I think if we do something like 0, I'm not sure this will work. Yeah, okay. So
Yeah, no, because it must be a constant.
yeah, but if there is a type that you want to add inside a block matrix, which is currently not supported, whether it's in a matrix or in a math, please ask us and we will try. The piece of code is quite nice and easy to add types, so it's perfectly doable. And so of course, I think the same won't work with FreeFEM, with PETSc math. Actually, it works. I'm not sure why, but anyway, we can add new types as needed. So if we go back to what's in the question, so in practice here, the F, B, and C blocks will be discretization of variational formulations, of course, so there will be sparse matrices. And so, as I mentioned earlier, in PETSc, the way to store block matrices is through a type called mat nests. And it's important, again, to keep in mind that it means that the matrix is not assembled by default. Okay, so we keep the representation of A as a global operator, but we don't assemble explicitly the matrix A. Okay, and so the same applies to this example. We can see that we have a mat nest. Okay, and so if we actually want to convert this to an assembled operator, maybe you want to then do some post-processing in MATLAB. Okay. There is a utility routine which is called mat convert, if I'm not wrong. AIJ, and then you can do mat convert of so the block matrix into AIJ. Okay. And so now if I do an object view of AIJ, I should have exactly the same format. Okay. So now the operator is explicitly assembled and stored in memory. And so you can post-process it in MATLAB or whatnot, and so on and so forth. But here with a mat nest, the operator by default is not explicitly assembled. We just keep it in PCs. So solving problems from CFD can be challenging. And in practice, if you deal with very large problems, you most often want to use a preconditioner. So in PETSc, there are tons of preconditioners that are available in FreeFEM. And for example, you can use a preconditioner which is called the pressure convection diffusion operator, which is an approximation of the inverse of the Schur complement, which can be computed through a mix of inverses of mass matrix, Laplacian operator, and so it's much cheaper to evaluate than the inverse of the exact Schur complement, which is not tractable in practice. Okay, and so when you look at a math paper and you see such an object, you say, okay, if I want to implement this in FreeFEM, of course, I don't want to assemble S-1 exactly, but I want to compute the action of S-1 as a series of operations of matrix vector product or matrix vector solution. And so that's what can be done in FreeFEM using a shell. And so, for example, this is nothing else than, let's say, 6 lines of code, and the implementation is quite straightforward. So KSP solves means solving a linear systems in PETSc. So we solve the first system with the input vector. We can solve in place. So we basically overwrite the input vector by the solution of LP-1 times input. Then we compute the matrix vector product. We cannot compute this in place. And then we solve the system with the mass matrix and we multiply the result by -1. And so this is the PCD preconditioner implemented in 6 lines of code, let's say. So there is some boilerplate code to tell to PETSc to use the function, but this is actual running FreeFEM code. So we can do the same for more sophisticated problem. For example, Pierre Marchand and Pierre Tournier are doing FEM-BEM coupling. And so in this particular problem, you are mixing problems from different discretizations. So it's not like OSIN where everything comes from FEM. Here you are coupling problems which are sparse and other problems which are coming from the boundary element method, which are compressed matrices. And so again, we have a very concise syntax, very much looking like the one you would get if you were to use a simple matrix type, let's say. And so you can do fancy stuff like solving a generalized eigenvalue problem using this notation. And so here in this scenario, AK, so the upper left block is a sparse matrix, so MPI AIJ. The R times the trace of the double potential, if I'm not mistaken, is a composite operator. So we don't want to assemble the product R times TDKM. We just keep this as a composite matrix. The mass matrix on the trace of the mesh is an assembled operator AIJ sparse matrix. And then the single layer potential is a compressed hierarchical matrix of type H2. Again, if you don't know a good preconditioner for this, for example, you can convert the matrix to a sparse matrix, and then you can use the LU method, for example. But of course, the SK is a dense operator, so it will be costly, but for debugging purposes, it works perfectly. So I will just mention that we are trying to be as economical as possible when it comes to storing operators. And so just previously, I showed you an example where one of the when some blocks are dense. And so in FreeFEM, there is an issue, for example, I mean, it's not an issue, but if you have, let's say, Lagrange multipliers as constraints, okay? In the previous example, I only had a couple of Lagrange multiplier, 2, okay? Now think about something with many more constraints, 10, 100, whatnot. In FreeFEM, we pay the price twice of the constraint because we store detranspose explicitly, and so it can be costly. In practice, if we use a MAT, we are automatically detecting whether the one block is the transpose of the other. And when it is the case, we can use a specific type such that the matrix is not stored twice in memory. Okay, so these are quite low-level optimization, but when we are dealing with problems with many Lagrange multiplier or many constraints, it can make an impact in terms of memory consumption. Ok, j'ai jusqu'à quelle heure?
Jusqu'à la nuit. Théoriquement.
Okay. Okay, so this slide is new. It's very close to a slide I presented 2 years ago for the 14th FEM days, but basically it's an updated version. Interesting to you. And so these are the latest results. So I got them like this weekend or last week. And so I wanted to benchmark the available tools in FreeFEM for doing distributed mesh adaptation. Okay, so in the context of distributed mesh adaptation, you have to keep in mind that everything is distributed. We never have a global full mesh. We start from a distributed mesh, and we never assemble a global mesh on a subset of processes. Everything is distributed from start to finish. And so this is a famous benchmark. So this is the Fishkara corner, so a re-entering corner. I don't want to do any complex physics on this problem. So for the moment, I just solve Poisson's equation. So this is solved using an algebraic multigrid solver. And so this is with 128 MPI processes. And again, everything is done in parallel. And so I use MSHmet, which is available in FreeFEM, for computing a metric after each solve, and then I adapt my mesh according to the metric produced by MSHmet, everything in distributed fashion. And in the benchmark, I'm basically trying to look at the performance of the tools available for parallel mesh adaptation. And so this is mostly, so the time to solution will be mostly driven by the software called PETSc, which is a tool for doing parallel mesh adaptation from area. And so at each step, I basically decrease the error I want to, the error finer mesh. I interpolate my previous solution on my new refined mesh, and I repeat the process, everything in a distributed fashion. So we start with a rough mesh of for 47,000 tetrahedra. ParMMG can adapt this mesh in 2.6 seconds. Then we need to perform the mesh, the solution interpolation from the previous mesh to the refined mesh. It takes 2.8 seconds, so it's not very optimal. And then we solve the linear systems with an algebraic multigrid solver. And so this step is extremely easy because I'm just solving the Poisson equation. But if you have a more difficult constitutive law like Navier-Stokes, you can imagine that this is much higher in terms of ratio with respect to ParMMG and the mesh transfer. And so I iterate, and at each step of the process, I basically make the mesh finer and finer. And so you can see that the number of tetrahedra is increasing. And so after 6 iterations, we basically go higher than 2.2 million tetrahedra. And in fact, if you are willing to pay the price, so I think it's about 10 minutes for the mesh adaptation, you can actually generate fully distributed mesh, unstructured mesh with FreeFEM. Okay, and so this is something which is very not trivial. So 2 weeks ago, I was speaking with someone from Lawrence Livermore National Lab. They have a huge finite element package which is called MFEM. It's used in the DOE for doing very large large simulations. And to this day, they have no tool for performing large unstructured mesh adaptation. They do forest of oak trees, so they do AMR, but they don't know how to generate unstructured parallel mesh. And so in FreeFEM, I think we have the edge. We are able to do something quite large in a fully distributed fashion. Okay? And so, in fact, this example has been in the distribution for quite some times. It's available in example HPDDM, Laplace adapt. So there is one script which does the mesh adaptation with MMG in sequential. I mean, the mesh is centralized and then spread again. And there is one which does everything from start to finish in a distributed fashion, and it's adapt dist. So if you want to run it, you can do it. And so this was generated last week because the MMG version got bumped. And so two years ago, when I presented initial results, ParMMG was a little bit not so robust, let's say. And so things are nicely improving. So 2 years ago, I was not able to generate such a large mesh, but it was not a problem of FreeFEM or not a problem of PETSc. It was a problem of ParMMG, and things are now getting more robust. So they are improving, and so hopefully next year I will show you 1 billion tetrahedra. Okay, it will take me probably 1 hour, but if we are the first to be able to generate with FreeFEM, MMG, ParMMG, and PETSc an unstructured mesh with 1 billion tetrahedra, I think it will be quite impactful. Okay, so I have some time left, and I will focus on the part that I'm most fond of, let's say. And so this is domain decomposition method. So for now, I've mostly focused on the tools surrounding PETSc, FreeFEM, so how to define block matrices, how to do parallel mesh adaptation and whatnot. And so a bulk of my work is also on how to solve linear systems efficiently. And so at the LGLL, we have been using FreeFEM to benchmark and to prototype new tools for domain decomposition method. mostly with Frédéric Nataf and Pierre Tournier. And so it has been very helpful into designing new preconditioner and new methods. And so I will give you a quick overview of how this works and what we can do in FreeFEM. And so to motivate you for the need of efficient preconditioner, I like this picture because it shows you that the default method in FreeFEM, which is an LU solver, it works very well. But as you increase your number of unknowns, so basically as you start to mesh larger and larger domains and whatnot, you have to pay a huge price into solving the linear systems with an exact factorization. Okay, so this is with the lowest order Taylor root finite element for an elasticity problem and a Stokes problem in 3D. And so it's purely sequential, so just a single process. And so this is using MEMS. And so MEMS, one can argue that this is the state of the art when it comes to linear solver. But you see that you have to be okay paying a price doing exact factorization. And so now, of course, you can do parallel computing. But even if you switch to parallel computing, these algorithms are quite difficult to parallelize. And so, for example, here I'm showing the scalability of MEMS using an increasing number of MPI processes. Okay, and so you see that if you go, let's say, above 128 MPI processes, it's very difficult to reach ideal efficiency. And with FreeFEM, we are routinely running problems on more than 1,000 processes. And so it will be difficult to use MEMS or any sort of exact factorization packages when we run such simulations. So of course, they've made tremendous progress into ways of making exact factorization less costly. For example, using a tool which is called block low rank factorization. But it turns the exact factorization into an approximate factorization. And so basically you are switching from an exact method to an iterative method. And so you are doing preconditioning, okay? And so I will show you our way of doing preconditioning instead of using MEMS for doing preconditioning. And so our way of doing preconditioning is through what we call overlapping Schwarz method. And one of the big strengths of this method is that it fits within the finite element framework quite naturally. Because let's say you have your domain omega, then when you do distributed memory parallelism, instead of assembling your matrix A on omega, you will need to do mesh decomposition. And so the idea of domain decomposition as a preconditioner is to match with the domain decomposition that was used for performing the finite element analysis in parallel. Okay? And so just as before, instead of assembling A on a global domain, we just assemble sub-pieces of the problem. And using those sub-pieces, we can define a preconditioner. For example, the additive Schwarz method, which is nothing else than the summation of the local inverses of each sub-problem. Okay? So these methods have been established for quite a while. There is a more recent variant, which is called the restricted additive Schwarz method. I won't go too much into the details. It's just a small variant. But one of the weaknesses of those methods is that as you increase the number of processes, so as you increase capital N, they tend to be less efficient from a preconditioning point of view. So it will take more iteration to converge. And so basically the assembly will be very efficient if you increase the number of processes. But then when you go back to the solving step, you have to pay a price. And so it's difficult to use in practice, let's say. So this is just what I mentioned here. There is no guaranteed scalability for a large number of processes. Okay, so what we do is course correction. So maybe I will skip this because it's not really important. I will focus on some results afterward. What's important to keep in mind is that we use a course correction which is similar to many fields in scientific computing. So this is a framework which holds either in domain decomposition method, in deflation techniques, in multigrid methods, and so on. So you may have seen this in some other field, reduced order modeling, it's everything is can be boiled down to basically this formula. And so there is $1 million question, which is how to choose the proper vectors to define the preconditioner, but I will not give you, I will spare you the details, let's say. So everything that I've shown is available in a library which is called HPDDM, which is basically the result of my PhD work here under the supervision of Frédéric Nataf, Frédéric Echt and Christophe Prudhomme. And so this library has evolved since then. It's used in FreeFEM as the glue basically between PETSc and FreeFEM. So HPDDM sits in the middle, and so it's usable by FreeFEM, it's usable by PETSc, and that's about it. Okay, I won't. So the advantage of the domain of such domain decomposition method is that they are called adaptive preconditioner, in the sense that we can make the method as robust as we want, but of course we have to be willing to pay a price. So for example, here we are solving a linear system with a threshold parameter tau, which specifies how strong how robust the preconditioner must be. So the lower the value, the less robust it is. And so we see that so if we don't use any course correction, basically the one level method is not very scalable. It's not at all scalable. And so as we increase tau, we make the preconditioner more and more robust. But of course, it makes the course operator larger and larger. And so it's costlier and costlier. Okay? So when you think about preconditioner in FreeFEM, it's not specific to HPDDM, to domain decomposition method and so on. It's always a matter of trade-off. So there are preconditioners which are very cheap to assemble, but that will require many iterations for the solution phase. And there are preconditioners which are extremely costly to set up, but that will converge in just a couple of iterations. Okay, and so it's very problem dependent. I'm not claiming that whatever I'm presenting here will work for your methods, but if you have some specific problems and would like to know what is the best preconditioner or how to find something which is not too costly but still converge quite fast for your applications, please let us know, and we'll be happy to help you out. So for example, here I'm comparing our method, so HPDDM, again, two state-of-the-art solver, so Boomer AMG and GAMG. So we can see that the time to the number of iteration is roughly the same, and so these preconditioners for now are much easier to set up. So if you are able to solve your problem with either Boomer AMG or GAMG, it's available in PETSc, it's available in FreeFEM. If you are able to do it because these are usually the fastest solver. But of course, there are other problems where the algebraic multigrid solver won't converge, and so we have some problems where our domain decomposition preconditioner are actually working quite well. This can be used also for nonlinear problem. So this is another example in this distribution, which is called, if I'm not mistaken, Bratu-HPDDM-PETSc 3D.edp or something like that. And so it's quite robust with respect to the coefficient, with the distribution of the coefficients, and everything is automatically handled for you as a FreeFEM user. You don't have to deal with writing the Newton method by hand. You don't have to deal with assembling the Neumann matrices which are needed by the preconditioner. It's the interface with respect to FreeFEM and HPDDM is quite transparent to the user. So you are more than welcome to try it out. Okay, and so as I mentioned, the method is very robust. And so here you can just see the convergence histogram of each linear system for a series of four. Okay, I will skip this. I will skip this slide and I will focus on the last one, I think. But basically, we can introduce for saddle point systems where we need to couple problems for one block and for an approximation of the Schur complement. So if you are interested, there has been a paper by Frédéric and Pierre in 2022. And so this has been implemented both in FFDDM and in HPDDM. And so I will skip that part. I will just show you some results. For example, on such a domain, which was generated by Loïc. And so on this domain, Loïc was interested in solving the Austin equation. And so the problem is quite large, so 100 million degrees of freedom with 1000 MPI processes. So you can try to use MEMS, for example, for this problem if you don't know anything else. The likelihood that the solve will complete is quite low because performing an exact factorization of a problem of 1 million unknowns will usually require much more than 1000 MPI processes. And so anyway, with the domain decomposition methods that we have at hand, we can solve this for various values of viscosity of Reynolds number. And so those methods are quite efficient. And again, you can couple them in various ways. So I won't enter too much into the detail, but as you make the Reynolds number higher, you can have some problems, but we have ways to deal with those problems, let's say, such that the preconditioner is robust no matter the viscosity. Okay, so just to wrap things up, FreeFEM is a fantastic tool for doing multi-physics solvers because it has a very high level of abstraction. You can build block matrices very easily with a syntax that looks like MATLAB or that actually looks like the actual formula in your papers. So the level of abstraction is quite high. And we can leverage the versatility of PETSc for dealing with various types, various preconditioners, various nonlinear solvers, and so on and so forth. This can be very useful if you want to compose solver. So, for example, if you want to do fluid structure interaction, you can spend some time working on the fluid solver, spend some time working on the solid solver, and then you can couple them quite naively, and quite easily with all the FreeFEM and PETSc machinery. Again, you can look at the tutorial, which is specific to the parallel part using PETSc. We are very grateful when you let us know when things are not working, because there are probably some bugs, and without your help, it's difficult for us to know all the bugs. So if things break or if they work, please let us know. So Frédéric mentioned the community. There is also the GitHub if you want to post a GitHub issue. Of course, you can reach out to us in private, but it's best if we try to emulate the community and have more people involved, let's say. When it comes to PETSc and SLEPc, there are also communities. You can post an email to the mailing list, or you can post a GitLab issues. If you have issues specific to HPDDM, you can reach out to us either through FreeFEM, through PETSc, or also on the dedicated HPDDM repository. And thank you for your attention. Sure.
Is it possible to manage moving meshes in distributed mode?
Yes. So, so what do you mean by moving meshes? Do you mean like the move mesh keyword? Move mesh. So the move mesh does not work in parallel. We could think of adding in the macro in this file. In this file, there is something like a convect parallel. So convect is another keyword which does not work by default in parallel. And so there is like a copycat of convect, which is supposed to run in parallel in the file macro.ddm, which is called convect parallel. So we could think of adding something like move mesh parallel, which will then work for distributed mesh. What you have to be careful about is that when you move the mesh, we cannot guarantee for the user that the field which is using to move the mesh is coherent among MPI processes. So if you have, for example, a mesh like that which is divided into process. And you have, for example, this process which says to move mesh using a field like that, and then you have this process which says to move in like that. So you have to keep in mind that you have a small buffer region here, and so in the middle it will generate garbage. And so many algorithms can be performed in parallel, but the big question is how to ensure that the user is not feeding incoherent field. And so we can come up with a solution, but it will not be ideal, and in particular, it will imply that you are in charge of feeding a coherent displacement field for moving the mesh. If you are okay with this, then we can make that, I think.
I have a question probably related to moving mesh. It's like when you have two meshes, or and you can, if you have a solution, you can sort of interpolate from one to another. But my question is, if we have a problem, a monolithic problem, variables that are not defined on these two meshes, can you sort of solve that problem? I mean, unknown variables defined on this mesh, and you want to solve the whole block monolithically in a. You parallelize that. It's a specific example like the composite finite element. So if you decompose the mesh, all these variables are unknown. How do you communicate and transform into length?
So
That's possible to be parallel.
that's possible, but it's so you lose some of the nice things about FreeFEM, which are that the scripts are very concise. It's more difficult. So it's not specific to FreeFEM. In many packages where, for example, you need to deal with contact, or where you need to deal with monolithic problem coming from a sub-region and stuff like that, having this work in a distributed fashion it can be quite difficult. Because the decomposition will not necessarily be the same on the sub-mesh or on the large mesh and so on and so forth. In any case, it's possible. There is an example, I think it's called it's called the restriction, sorry. And so in this example, we basically start from a sub-region, and so everything can be done monolithically, but it requires some bookkeeping for letting PETSc know how the doves are related one with another. And so it's possible, but you will see that most of the examples that are doing like that, also for free structure interaction, for example, the issue of locating point and locating degrees of freedom in a distributed fashion is difficult. And so the scripts are difficult, but it's possible.
So now you have this composite finite element. I can see that there's an example.
Yes.
Does that only work for the sequential case?
No, it works in parallel. Yes, with PETSc.
Okay.
So for the moment we keep. So Pierre will correct me if I'm wrong, but for the moment we keep a global mesh and we perform a local assembly on the global mesh. And so it's slightly suboptimal in the sense that each process has to know the global mesh. And so that's the only small limitation that we are not 100% sold on the idea of whether we need to.
Do you have an example for this parallel example?
So all composite examples should run either in parallel or in sequential. So you can just increase the number of processes and you don't need to change the script, and it should work.
So I can also apply this preconditioner.
So
in HPDDM, there is a composite example.
Yeah, this one. So yes, you can use all the preconditioners you want that are algebraic. And so that means, for example, Hyper or GMG, so the algebraic multigrid. You can use LU, Cholesky, and you can use field splitting, where PETSc is able to detect that the problem comes from a structure, like a saddle point problem. If you want to use preconditioners that are for example, coming from domain decomposition method, like for example, optimized Schwartz method, or HPDD, some part of HPDDM, then it won't work. But you can still use a lot of methods. So of course, it's one way to start learning about PETSc, its options, and so on. So yeah, that's perfectly fine.
Okay.
If I don't get wrong, so the numerical performance of HPDDM will relies on the mesh partitioning, right?
So we try to make the method as robust as possible, independently of the domain domain decomposition. But of course, depending on how the domain is decomposed, if you fix the quality of the preconditioner, it may need to select more a larger coarse operator, and so it may be more costly to assemble. But the numerical performance is supposed to be fixed, no matter the domain decomposition.
So is it based graph-based or bisection?
For the domain decomposition, so most of all the results I've shown are using METIS for the domain decomposition. So it's like a nested dissection of the graph, and
I wonder if we use some hypergraph or SLEPc.
Yeah. So again, since the method is supposed to be robust with respect to the decomposition, this is an area that we have not very investigated, but it could be interesting indeed to look at the actual performance as you change the domain decomposition. But you could make the method as robust. It's a matter of costs for assembling the preconditioner that will change.
Okay, so it's time to the lunch. So thanks again, Pierre. So we have the lunch at the same place of the coffee break. Tiens, je vais te demander un truc. Je n'ai pas le temps de noter ton site web.
Je te le fais si tu veux. Ah, attends. Ouais, non, mais t'inquiète pas, je m'en occupe. Je mettrai aussi un titre, parce que là, pour l'instant, c'est TBA, mais il n'y a pas de souci, je le fais.
On verra ça. Ok. Tiens, on va couper l'enregistrement.
Je te laisse faire.
Ça sert à rien d'enregistrer.
Okay. So this is not related to finite elements, and so now the idea is basically to distribute our workload according to the number of processes. So how we can do this? First, we need to First, we can define a mesh. Okay, so I will assume, for sake of simplicity, that we are dealing with a Cartesian mesh, a square of dimension 100 by 100, for example. And the idea will be to partition this mesh. Okay. So if I plot this, if I run this, I should see nothing special. Okay, in fact, I don't see anything. And so that's because by default, FreeFEM MPI does not activate graphics. And so you need to force graphics. And the flag for forcing the graphical interface is the -WJ, so with graphics. Okay, and I see my global mesh. So here the mesh is quite simple. So we could think of a partitioning, like a Cartesian partitioning, we have 4 processes, we have a nice square, so we could divide this into 4 equally sized sub-square, let's say. But of course, it's not very general. It does not apply to distributed memory computing and so on and so forth. So in practice, we can use a mesh partitioner or a graph partitioner. And in FreeFEM, we have 2 types of graph partitioner, Metis and Scotch. So we need to partition this. Either through Metis or Scotch. So I will use Metis, but again, you can use Scotch if you prefer. And so Metis is not part of the distribution of the default distribution. It's an additional plugin, and so we need to load the Metis plugin. Okay. Now, if you are running this on your own machine, so it's a good time to check whether you have the Metis plugin installed. Hopefully, it's running okay. You can just run the same binary just to make sure that the load Metis plugin is okay. And here I have no issue, so it's running okay. So the Metis plugin can be used to partition a mesh, and the partitioning of a mesh is nothing else than an identifier of each of your grid, of each of your elements, according to a specific color. And so in our case, we have 4 processes, and so we want to partition our domain in 4. So we can use Metis, and so the API is Metis dual because it's using the dual graph of the mesh. And so the API, I'm always confused, but it's okay. It will take 1 or 2 tries, I think. So I think first it's the name of the mesh that we want to partition, so TH. Then it's I think it's the number of partition that we want to have, so MPI size. And then, if I'm not mistaken, it's the partitioning tag. And so the partitioning. And so the partitioning, what is it? It's nothing else than an array which marks all of the triangles or tetrahedrons in 2D, in 3D, sorry, with a specific color ranging from 0 up to MPI size -1. And so we can define partitioning in multiple ways. For example, we can define partitioning as a P0 function. So a P0 function will be constant per element. And so we can define this P0 function using the keyword FSpace. Okay, so FSpace, PH, defined on the mesh TH, and then P0. Okay, so this is used to store our partitioning, which is constant per element. Okay, and so now we define our function living on the FSpace, so PH partitioning. Okay, so if you know a little bit about FreeFEM, you know about the famous trick for treating finite element functions as arrays of vectors, arrays of degrees of freedom. Okay, so here partitioning is a finite element function. For example, we can interpolate. For example, can be used to interpolate analytic functions. So, for example, we can do partitioning equal x squared plus y squared. And the function can be also treated as an array using the partitioning bracket notation. As an array of unknowns with the bracket with the notation. And so here in practice, we want to use the the bracket notation because we don't care about the finite element properties of the array. So we do partitioning. Okay. So does that work? Unlikely, but let's try. Okay. So I think I got the order wrong. It's first, no, sorry. It's first the array, then the mesh, and then the number of partitions that we want in the array. So first the array. Yes. How did I guess this? So okay, so this is very expert, in fact. So so the first line is the error, and so the error tells us that we have an operator opening with a parenthesis. So basically, our list of arguments. Oops, sorry. Our list of arguments here is this. Okay, so how to decipher this? So you have to guess if you don't know by heart. And so here, for example, you see FEM2D mesh. And so you can guess that it's a two-dimensional mesh. Then you see L, which means long. Integer in FreeFEM are stored as long. And then you can see P2 KN IDE. So in FreeFEM, KN stands for one-dimensional array. KNN stands for two-dimensional array. And then you can see D, which stands for double. So basically an array of double. So this is in fact perfectly matching with what we use. So we have mesh, then number of partitioning, then array of double. And here we have indeed mesh, integer, and then array of double. Okay. And so then list of choice, FreeFEM tells us what are the possible choices. Okay, I will rerun just with a single process so that it's less of a mess. We can see that the list of choices are, so whatever comes before the double column is the return type. So I won't care too much about the return time. What I will focus on is the last part. And so the last part, you can see that we can partition, so KNL, again, an array of long, an array of integer. Sorry, the parameters are in order, first an array of long, then a mesh, then a long. FE base, that means that it's a finite element function. So it's not very important. I will focus on this part. We can see that we can also have as input parameters, so KN double, an array of double. For partitioning, this time you can see mesh L. So this is a linear mesh. So we can call metis for partitioning a mesh L. We can call metis for partitioning a mesh S, a mesh 3, and so on and so forth. So it takes a little bit of trials and error to figure out what are the types. But you can, when you get used to it, you can try to decipher automatically. But it's yeah, it's a little bit difficult, but that's one way to do it. Does that answer your question? So yeah, what you most often see is basically FEM2D 5 mesh, FEM2D mesh S, FEM2D mesh 3, KN. KN is always a single dimensional array. KNM is two-dimensional array. So actually we can try this. If we put, for example, a real int KNM 0, 0. Here we should get also a nice error. KNM. Yes, so KNM, so two-dimensional array of double. It's not perfect, but after a while you get used to it. Okay, and so our mistake was that the input parameter was at the beginning. Sorry, the output parameter was at the beginning. Okay, so the code is running. I want to check my partitioning, so I will just plot partitioning. My partitioning into plus MPI rank, no, sorry, MPI size subdomains. Okay, so I'm calling these subdomains. It's not specific to domain decomposition method. It's just the natural lingo for distributed finite elements. Even if you decompose the mesh into subdomains, it does not mean that you have to stuck with domain decomposition preconditioner afterwards. You can do exact factorization. You can do algebraic multigrid. It's just the name of the small pieces of the domain. Okay. And so now if I run this, okay, maybe with 4 process and with graphics turned on, I have my decomposition into 4 subdomains. Sorry. So this is subdomain 0, this is subdomain 1, in blue 2, and in red 3. And so you can see that the partitioning, it's not random, but we have no special control over the decomposition. We can enforce some constraint to make the decomposition geometry specific, let's say, but by default, we don't force anything.
How do you force the graphic blocks?
It's the -WJ. So yeah, keep in mind that FreeFEM MPI by default does not have graphics turned on, and so you need to add -WJ with graphics. Okay, and so this is very the foundation of distributed finite elements. And so it's the same in many finite element code. So even if you are not familiar with FreeFEM and use some other finite element code, I don't know, Deal2, Dune, Firebreak, Phoenix, whatever. All these packages use the same principle. They first start by subdividing a mesh into sub pieces and then do everything in a distributed fashion. As I mentioned this morning, there are some parts that are not trivial to parallelize, but when it comes to the assembly, we can do it quite efficiently. So this is what we will focus on next. Okay. Okay. Oops, sorry. So there are some steps which are independent of the partitioning, let's say, and so that's one of the strengths of FreeFEM, for which you can define abstract object. And so, for example, we'll start with the basic stuff, which is the variational formulation. And so, just as in sequential FreeFEM, you can define a varef, but not necessarily use it right away. And so we'll start with this so that we can forget about it later on. And so for the beginning, as I mentioned in the beginning, we will try to solve a Poisson problem with a Lagrange multiplier for imposing some constraint. And so I will call this V Poisson. And so this will be a scalar problem. So the unknowns will be U, the test function will be V. And so I will just do into the th dx of u times dx of v plus dy of u times dy of v plus some source term into the th f of v, let's say. And so for the beginning, I will just impose directly boundary conditions for debugging purposes, let's say, on 1 u equal, for example, 1.0. Okay, and so for good measure, I will just solve this in sequential for the beginning, just to make sure that I have no issue in my varef. And so I'm guessing most of you know about FreeFEM. And so in FreeFEM, if you want to instantiate a variational formulation, you can do matrix A. So I will put this into a bracket. Matrix A equals V Poisson. The name of, okay, so I need to define my FE space. And so for the moment, we will assume that we use, for example, piecewise linear finite element. I will call it, I don't know, VH. And so the name of the mesh is TH P1. Okay, so now I have my FE space and I can instantiate my variational formulation using VH. So it's the bilinear form. So I'm using the same function, finite element function space for the unknowns and the test function. And I can also instantiate my linear form using the famous V Poisson 0 as unknowns VH. Okay, so again, this is the expert tutorial, but just as a reminder, when you want to, so first for variational formulation, you need to always split the bilinear part and the linear part. And you also need to ensure that the bilinear part is a linear problem. So we cannot do, for example, dxu squared, something like that. If you want to do that, you need to do the linearization yourself. And then when you want to assemble the bilinear part, you need to use the name of your varef followed up with the two finite element space. And for the linear part, you can just put 0 as the unknowns. So I need to declare the variable f, that is correct. I don't need to declare the variable u and v, however. Actually, I'm not sure, but I think we don't. But for f, yes, let's put func f equal something like 10. Okay, so I want to make sure that the code compiles. Okay, so for now, everything okay. And so if I'm using a problem instead of a varef, then I need to declare u and v. Then I need to declare u, v, but not needed with the varef.
Okay, but what do you put for braces? On the
Where?
Before and after the two last lines.
Ah, okay. So this is just for scoping. So FreeFEM resembles C++ and C in some instance. And so when you put brackets, it's useful, for example, to scope a variable. And so, for example, here that is useful to ensure that the variable matrix and the variable RHS are freed and suppressed when reaching the end of the scope. And so here, memory for A and RHS is freed, and we can reuse A and RHS. So for example, we can do something like string RHS, my right-hand side. So it's just a small optimization trick. If you want to make sure that the memory is freed at some place in your program instead of keeping the variable alive throughout the full execution of your program, you can use curly brackets just for good measure. Okay, so for now, no. For now, I'm just solving the Poisson problem. And so in sequential, and so I do VH solution equal A-1 times RHS. And I want to make sure that the solution is the proper one. So I will plot my solution. And so this is the sequential solution to the Poisson problem. Okay. So let's see what we get. So we can run this with a single process. And we indeed get the solution of the Poisson problem with the Dirichlet boundary condition just on one side of the square. Okay. So I guess now is a good time also to tell you about the way we impose directly boundary condition in FreeFEM. So maybe I can show you something. No. Elimination. Okay. So by default in FreeFEM, we use what is called penalization to impose directly boundary condition. And so this is the last line of this slide. So so if we assume that the unknowns are partitioned in two sets, so JD for the unknowns which are not associated to directly unknowns, and JD bar for unknowns not associated to directly unknowns, and JD for directly unknowns. By default, we add 10 to the power of 30 on the diagonal. We multiply the directly unknowns by 10 to the power of 30, and we solve this system. And so because we are using double precision scalars, we can be sure that the solution is correct up to machine epsilon. There are some other way to impose directly boundary condition in FreeFEM. And for example, we can perform non-symmetric elimination. And so instead of using 10 to the power of 30 on the diagonal for the directly unknowns, what we use is the identity matrix on the diagonal of the directly unknowns and put 0 on the associated columns for all rows associated to directly unknowns. For performing this sort of non-symmetric elimination, we can adjust a variable which is called TGV, which is a global variable defining all FreeFEM scripts. And so we can define it at the beginning, for example, and we can say TGV equal -1. Okay. So you don't need, actually, you should not do something like real TGV equal -1. This will define a variable TGV in your script. What we want here is to access the global keyword of FreeFEM, which is already defined for you. We can do TGV equal -1. So there are some other keywords. For example, we have access to the verbosity. So you can set it on the command line, but you can also set it in your EDP script. So this can be useful, for example, if you want to switch back and forth the verbosity. For example, you can have a large verbosity here. I mean, large. We can try. Okay. And so, of course, the way we impose the directly boundary condition should not impact the solution of the linear system. And so here we get the same solution. And so we see that we have slightly more output when we use the verbosity surrounding the creation of the mesh. So I will just use that for process 1 and 0 otherwise. So a global identifier, not define it. I mean, you can define it, but at your own risk. And so the same for verbosity. Okay, so the solution, so for now, Poisson with directly boundary condition is fine. We are solving it with in sequential. So if we run the same script but with, for example, 4 processes, why did I quit? Sorry. If we run the same script with 4 processes, the same problem is being solved independently on the 4 processes. Okay, so there is currently no parallel computing. I mean, there is parallel computing, but just doing the same binary, the same code on 4 MPI processes. So not very interesting in my opinion. So now we want to actually break down the domain according to our partitioning. And we want to make all the computations in parallel, both for the assembly and for the resolution of the linear system. So as I mentioned earlier today, we have so we can do it. We can do it with the recent composite FE space and even some merges in the FreeFEM kernel. I will show you how to do it with the macro_ddm.cdp because it will follow the distribution, the geometrical decomposition, let's say. When you let FreeFEM do the parallelism itself, the matrix is broken down at the algebraic level, and so it's a little bit more difficult to see the link between the Métis decomposition and the actual the actual linear system. And so for this, I will have to include my the small file I mentioned this morning, so macro_ddm. Okay, again, it's a nice moment to check that you have a functioning FreeFEM environment, and so it should run just the same. Okay, no problem. So I have everything I need.
For the plot,
Yes.
doesn't plot for all the 4 processes.
No, so the plot is one of the few commands of FreeFEM which has only which can be only run on the first rank. So the FF_GLUT, so the graphical window can be only opened by the process rank 0. So for example, if I do something like if MPI rank equal 1, here I should get no, I don't have the partitioning. However, you still have access to the SVG and PDF command, I think, and so you can do, for example, my plot from rank 1. And so here I have the file. But yeah, the graphical window can be only opened up by process number 0.
Also, you can use medit as a plugin.
Yes, correct. So medit, so load medit. It works for 2D mesh. And so here, for example, else if MPI rank equal 2, medit, and so again I always get the order wrong, but I think it's th.
It's just the final.
Okay, thanks. Okay. So, yeah, medit can be opened by any process. FF_GLUT can only be opened by the first process, and yeah, that's about it. Okay.
Okay.
Yes.
So based on this example, instead of -2, I don't get the same solution.
Yes. You want to know why?
Yes.
Okay.
I mean, it is interesting.
It is very interesting. And so the question is, if I use TGV equal -2, so TGV equal -2 does this to the linear to the matrix A. So it does not only set to 0 the rows, but also the columns. Okay. The big issue with TGV equal -2, and one of the reasons it's very dangerous, is that we don't do the lifting of the right-hand side. So we don't do this. And so basically TGV equal -2 will only work if you have homogeneous Dirichlet boundary condition. Okay, so we can actually try this in practice. Let's do TGV equal -2. I should get garbage, or maybe not. Yeah, I get garbage. I mean, not what I should get. And so now if I switch to an homogeneous Dirichlet boundary condition, so U equal to 0, then the right-hand side is has the proper value because JD equals 0, so we are good to go. And so now I get the proper solution. Okay, so TGV equal -2 should be only used for homogeneous directly boundary condition, or you can use also it for non-homogeneous directly boundary condition, but you need to fix the right-hand side yourself. So it's nothing else than a little bit of linear algebra. You just need to. It's possible. There are actually examples in the distribution where we do the lifting, so it's possible. But yeah, be careful with TGV equal -2. Okay. Let's see. Okay.
But that's difficult to implement the non-homogeneous boundary condition in FreeFEM automatically.
What's that?
I mean, on the right hand side,
Yes.
why do you have this?
This operation automatically?
Yeah, that's tricky.
Why don't we have it? Because two reasons. Frederick is a big fan of TGV equal 10 to the power of 30, so he did not bother too much with the other options. And a more technical reason is that if you want to shift, if you want to do the lifting of the linear form, you also need to have access to the bilinear form. And so inside the grammar here, it would be very difficult to be able to assemble RHS properly. So you need to provide, for example, something like do lifting of non-homogeneous boundary condition with the matrix A, for example.
Yeah.
So it links very tightly the bilinear and the linear form. And by design, these two operations are very decoupled in FreeFEM. And so basically it's...
But usually use in FEM software, when you assemble the matrix, local matrix, you just do this minus this local matrix on one side and add them up. That's usually how it's implemented in this FEM software. So when you assemble local matrix, at the same time you deal with this non-homogeneous boundary on the right side, just do it automatically, add them up.
There are many ways to do it. And so again, originally FreeFEM was mostly using TGV 10 to the power of 30. And so we added TGV -1, -2, but we didn't bother too much with TGV equal -2. Yeah, sure. But not all FEM software do this. So just yeah.
You can do it by hand.
Yeah, sure. Okay. Okay. So macro-DDM.cdp is a huge file. There is very little need for you to go into this file. You should just try to remember the basic commands, let's say. And so most of the commands in this file follow the PETSc lingo. And so the PETSc lingo is always something like, follow the PETSc lingo. And so in PETSc, when you want to create an object, for example, a mat, you do something like mat create. When you want to create a preconditioner, you do something like PC create. When you want to create a scalable nonlinear equation solver, SNES, you do SNES create, and so on. And so we try to stick to this lingo. And so in particular, the two most important operations are dmesh create, which can be used to build a distributed mesh. and so also mat create, which can be used to distributed matrix creation. Distributed matrix creation. So what I want to do now is to make sure that all the processes are correctly connected one with each other using the partitioning that I've created at the beginning using METIS dual. Okay. And so, okay, maybe I will start first by doing the simple one, which is just calling dmesh create. So what this does is just partition the mesh th. Okay, and so before that, if I do cout th.nt, and I do the same operation afterwards, okay, maybe just for rank 0. I should see that the number of triangles on my local mesh, so on my mesh th, is decreasing because the domain has been partitioned. Okay, and so indeed we start with a 20,000 local triangles, and then the domain is divided into 4. Okay, and so you can see that 4 times this value is slightly greater than 20,000, and that's because we use a small amount of overlap between subdomains, such that the finite element assemblies can be performed rather efficiently without needing any additional communication. So this is a little bit of the under the hood details. Just keep in mind that there is a small amount of overlap among MPI processes, among subdomains, to perform the finite element analysis more easily, let's say. So just I think there is a utility routine which is called plot dmesh. I think th cmm equal my distributed mesh. Okay. And so now we can see that we are using indeed a mesh with a small amount of overlap, which is again for performing the assemblies easily. If there is no overlap, then that means that we need to do some communication on the interface among subdomains. So it's a little bit more technical. There are some finite element packages that do without overlap. Some we do with, and so we do it with overlap. Sorry. So you can see that this partitioning somehow resembles this partitioning, but in fact we have not used the partitioning which was generated by METIS. And so we can force the use of a user-defined partitioning, I think, with this macro. So macro th user partitioning. And then the name of the function which is used for the partitioning. And so here we are using partitioning. Okay, so this is a macro. And so in FreeFEM, you know that to end the macro, you need the 2 forward slash to end the macro. Okay, I'm not sure this is working, in fact. So how to check whether it's working? Let me try to switch quickly to Scotch. So instead of METIS dual, I call Scotch. So the API is exactly the same, I think. Okay, we get a slightly different partitioning, and so it's working perfectly fine. So METIS was mostly developed in the US. So it's kind of abandonware now because the main developer is now working at Amazon. Scotch is developed in France at INRI à Bordeaux. They are actually starting a new consortium, so use Scotch when you can. Okay. Their purpose is basically the same. They are both graph partition. Okay, so this is just for creating a distributed mesh with a user provided partition. Okay, so we have created the mesh, and so now we need to make sure that the finite element space is properly distributed among MPI processes, because one of the drawbacks of using overlap is that, for example, if you look at, I don't know, let's say we are using P1 finite element. For example, the node that is below my mouse, we have to make sure that the value will be duplicated among two MPI processes because it's in the overlap region, and we want to make sure that the value is consistent among MPI processes. So we don't want the processes to perform independent finite element analysis. We want to make sure that they're actually solving the same problem. And so we need to create a distributed finite element space, which is not a FE space, but which is a distributed finite element space. So now if I do something like FE space WH, P1, these are purely different FE space. So these are independent local FE spaces. So any computation here is independent. Okay, and so in fact, as a toy problem, we can reuse everything here. And so instead of doing the assembly on VH, I do the assembly on WH. And so here, sequential independent. Okay. And so if I solve this, it does not work. So why does it not work? So process 0 is this one, the orange one, and we have that Dirichlet boundary condition only here. So with respect to Dirichlet boundary condition, the orange one is a floating subdomain, so there are no Dirichlet, so the problem is indefinite. For now, we have not added the Lagrange multiplier to make the problem definite. And so the linear solver just does not find the solution because, I mean, the problem is indefinite. So it's working as expected. Maybe I will just add Dirichlet boundary condition everywhere, just so that we can see that the problem is in fact solved just on a local subdomain. So here we have the global problem on the full metric, on the full mesh. And so if I perform just the solution step on the local subdomain, I get a solution which is not a restriction of the global problem. I'm just solving the Poisson problem on this mesh, but it has no link with the original problem. So we want to make sure that we have a distributed FE space where the unknowns are properly linked one with each other. So to do that, we've made a little bit of a shortcut. Instead of defining something like a DFE space, okay? we have made a shortcut of using the matrix operator. So a matrix can be seen as an operator which is discretized on an FE space. And so instead of defining a distributed FE space, we went directly to the mat structure. So we can define the mat, for example, A, and we need to tell FreeFEM how to make the link among subdomains, how to have all processes communicate one with each other. And so this is done using again the PETSc lingo mat create. And so for building a mat in parallel, just as when instantiating a finite element space, we need the name of the mesh. So here it's th. We need the name of the mat A, and we need the type of finite element that we want to use. And so I will use the same finite element, so P1. Maybe I will create a func pk equal P1. PK. Okay, so if you are running this live, it's always a good time to check that your installation is working. Okay, my installation is working, but I have a bug. Of course, mat does not exist. It does not exist because it's not part of the core of FreeFEM. You need to load the additional plugin PETSc. Okay. Things seem to be running. Okay. So of course there is not much stuff, but as I mentioned this morning, we tried to make the syntax as close as possible to a sequential script, and so now we can assemble inside our mat our variational form, and so we can do R equal R varf, so V poisson, VH. We can reassemble. Sorry, it's VH. We can reassemble our right-hand side. And we can solve again our problems. So this is not very interesting. I will just put this inside bracket, if 0. And this is not very interesting as well, if 0. Tac. So my solution, A, this time it's a mat times RHS. And so this is now parallel solution to the Poisson problem. So I will run this now. Okay. Okay. So the identifier RHS exists. It means that I have already RHS defined somewhere. Where is it defined? Okay, of course. So this was just for educational purposes. So I will just remove this. Oops. And so now it should be better. Okay, line 57. What is the issue? So basically it tells us that I cannot do both the definition and the affectation, the definition and the initialization together simultaneously. So I need to break this down in 2 steps. So I should fix this probably, but this should work now. Okay. So the code is now running. But of course, you see that we only have part of the domain, so it's not very interesting. And so there are 2 ways to fix this. One way is to again call a small utility routine, which is inside macro DDM, which is I think plot D, I think. But then I need does that work? I don't remember. No, I think I need to use the mesh parameter, so th sol cm. Okay, so this is the distributed solution. This is one way to fix it. And the other way to fix it is to use ParaView, which is actually much better if you want to do shiny pictures for your papers or for your presentation. And so the way it works is using a SaveVTK. And so I'm sorry, I'm always confused, so it will take a couple of tries, I think. SaveVTK, I think it's poisson.vtu, and then th sol data name equal name and order equal ff order. So name is an array string int name equal u, and ff order is an array of order, so either 0 for piecewise constant or 1 for piecewise linear, or higher order equal 1. Okay, yet another error. Where is this line? Line 60. Ah, okay. Okay, now it's line 63. And 63, what is the issue? Impossible to cast. So again, it's a mix. I'm getting the order wrong. No. Wait. Ah, okay. So actually, I should not define an array of names. I should just put the names directly. So data name equal u. Perfect. And so now if we do Poisson, open Poisson, so what the SaveVTK does in parallel, so in parallel, when you load PETSc, when you save VTK, when you call the SaveVTK command, it will save one VTU file per process, and it will automatically create what you can call a main file. So a main file will be a .pvd file, which can be used by ParaView to load up a distributed solution. So when you have multiple pieces that ParaView needs to load together. And so in practice, here I have the main file poisson4.pvd. And so now if I open this up, I have a solution, U, in ParaView. Okay, and just as on ffglut, you can see here the domain decomposition. I think maybe we can show we can remove them. Huh? So it's a little, so it's a trick to remove them. The trick is that, okay, this is very the technical stuff of macro DDM or all the tools for doing domain decomposition. But basically, when we have an interface which was introduced by the domain decomposition, so not 1, 2, 3, 4, all the other label, by default, I think the label number is a ridiculously low value, like -1. And so if you want to remove them, we can zoom to make sure. Okay, I think you see them. So now if we do, I think it's filter, alphabetical, threshold, and then we threshold by label. and we check, we check for the smallest value +1. And then it disappears.
The same line for 3D.
For 3D, it's more technical.
Yeah.
I think it's due to ParaView itself. So at one point it was working. I think with version 5.8. I think now it's 5.12 or 13. 5.13. And so now I think it's more difficult, but you can still make it work. But I think there is one extra step, and I'm not sure of what is the extra step. It's been a while since I did it, but it should be possible. Okay. And so, yeah, so of course, when you can, I strongly advise you to use the SaveVTK command. For example, it can be used to automatically generate movies. For example, let's say we want to solve with a different okay. So first, I remove all these, and let's say you have a parameter alpha. Okay, real alpha equal 1.0, or maybe we also have in the parameter in here, let's say alpha cos alpha times pi times x times y. Okay, that's fine. Okay, so you want to do a first solve with alpha equal 1, and then you want to do a second solve with alpha equal, I don't know, 10. So you want to solve you want to assemble again your linear part. So you just reassemble your linear part. Of course, you need to resolve your system, okay? And then you want to make a nice movie and to have all the plots together. And so again, you can use SaveVTK, and this time you need to add the flag append, which will automatically generate a master file or a main file, poissoncat.pvd with multiple files. Okay, so just making sure. Let's kill this. Let's kill this. Tac. We relaunch. Okay. Alpha already exists. Yeah, of course. Okay. So let's open the file, the ParaView file again. Open poissoncat.pvd. Tac. And so this is the first solution. Oh, sorry. No, this is the first solution. Ça, je t'avais dit d'enlever. No. This is the first solution, and this is the second solution. Okay. And of course, you can apply the filter, and it will apply everything. Tac, tac, tac. This one. Tac, tac. Okay, and so we have a nice movie. No, I'm not a ParaView expert, but you get the idea. Yes.
So can you explain a bit more about what happened inside the math create?
Yeah, sure. So basically, in Math Create, here. So what Math Create does is, again, try to interconnect all the pieces together. Okay. So before Math Create, if you do something like VH local numbering, and then you do something like local numbering equal, let's say 1 to local numbering dot n. So basically, you have a vector, you have a local vector defined on each process, and each process number its degrees of freedom 1, 2, 3, 4, 5 up to the number of local degrees of freedom. So now, if I plot this, I get something like local numberings of all processes. I get something. I get something like this. And so what we can see is that, for example, the leftmost process number unknowns like displayed, the process in the middle numbers unknowns like shown here, and so on and so forth. And so basically what MatCreate does is connect all the DOFs together. And so it gives a single identifier for each of the DOFs, whether they are in the interior of the subdomain or in the overlap region. And so to check the global numbering that it generates, there is a utility routine, I think, which is called global numbering, and then the name of the mat and well, okay, the name of the variable is a little bit confusing. I will just use that. And so instead of local numbering, I will call that just numbering. And so I'm not sure this will work, but we can see global coherent, okay, local incoherent numbering. Okay, and so let's check this. Okay, so this is all the local finite element space, all numbered locally.
Yeah.
No connection in between processes, so you can do your finite element analysis locally, but there is no link with the global problem, so it's not very useful, let's say. And so this is the global numbering. And so this global numbering is basically the permutation between the local to the global numbering.
But it's only the mapping between local. So there's no such thing of a global matrix. It's an imaginary global matrix.
Yes, yes.
Yeah.
So in practice, I mean, it's not very imaginary in the sense that so the global matrix is assembled by each process, and so each process is in charge of a small piece of the global matrix. And so we can actually have a look at the so-called global matrix. I think if we do mat view draw pose -1, draw geometry or draw size, I think. Perfect. Par contre, toi, je t'ai encore dit de te taire. And so, okay, so it's too big, sorry. Draw size 800. So this is the global matrix, but the global matrix is assembled, only some part of the matrix is assembled by each process, okay? And so in fact, it's very informative to look at the shape of the matrix. So I'm sorry, the dots, so the dots represent the non-zeros. And so it's quite difficult to see, but for example, here you can see that, so you have the main diagonal, okay? The matrix, of course, has a main diagonal. It's a Poisson problem after all. And so you know that there are connectivities depending on the connectivities of the elements. And so furthermore, when you think about distributed computing, there will be also connectivity depending on the connectivity of the subdomain. And so here, for example, you can see that there are some non-zeros in this part of the matrix. And so this means that the subdomain 0 interacts also with subdomain 3. Subdomain 0 also interacts, it's 0, 1, 2, 3. So 0 interacts with a little bit of 1, a little bit of 2, and a little bit of 3, I think. Subdomain 1 here interacts with a little bit of process 0 here, a little bit of process, no process 2, I think. But anyway, by looking at the structure of the matrix, the global matrix, you can get an idea of the connection between subdomains. You're welcome. And yeah, again, so this is PETSc, the matrix A, and this is FreeFEM, the mesh and the finite element numbering. And so there is a one-to-one correspondence between the assembly of the matrix according to the finite element numbering. So of course, we can so this is working. We can also try with P2, for example. It should work just the same, maybe slightly more non-zeros in the matrix, and so we can maybe see things better. Yeah. So process 0 is connected. Oh, sorry. So the visualization is not ideal. Subdomain 0 connected with subdomain 1, 2, and 3. Subdomain 1 connected with probably 2, 3, and 0. I mean, almost all subdomains are connected with each other, except for the top and the bottom. But I think you get the idea.
These comments that you type to
Okay. So again, this is a little bit of a technical question, but I'm happy to answer. So if you let FreeFEM compile PETSc for you, which is not your case, I think.
Yeah, no, I probably
Anyway, I will for the sake of completeness, if you let FreeFEM compile PETSc for you, you can see that by default, if we go in FFPETSc, and if you go into Makefile, you can see that by default, no, sorry. By default, we deactivate X, so the window manager. And so if you let FreeFEM compile PETSc, this command draw will not work. It will say that PETSc was not compiled with X window support or something like that. If you are working on a machine where you have compiled PETSc yourself and there is an X window installed, which is the case for almost all Linux machines, and on macOS you need to have X quartz, but that's possible. Then you can let PETSc do some plottings. Not only the matrices, not only the matrix entry. You can have PETSc plot eigenvalues, Krylov residual, and so on.
You have several matrices, several PETSc matrices.
So here I think I have a single one. Let me just, we will do something. We will try this. How can we try this? Interesting problem. I will create both matrix discretized with P2 and one with P1. And so what I should do, okay. So FE space LH one mat B. So it's a new mat because it's a new FE space. So I need to create a new mat, and so I can do mat create THB LH. And of course, I need to reassemble everything because again, it's not the same problem. Where we are at. Okay, I will copy. No, the variational formulation remains the same, sorry. But I need to reassemble my varef with my new FE space, so LH, LH. I need to resize my right-hand side because now the number of DOF is not the same. So RHS.resize LH.endOF. And then I need to update my solution vector. So maybe you are familiar with this little trick, but I need to update the size of my solution vector. And so now I need to solve TAC. Okay, let's be even more fancy and switch the alpha yet again. So maybe it was 10, we go to 30. And so now I think everything is set up. Of course, now I need to solve for B. I can continue my small animation. Tac, tac, U, poisson. th sol, everything is set up. Okay, and so now what happened? Tac, okay, first an error. Which line? Where is it? Ah, of course. Thank you. Sorry. Okay, and so I think so it will depend if you are on Windows, on the Mac OS or Linux, but on Linux you can just click on the mat and it shows you the next one.
Oh.
It's just like FFglut.
So inside, so there is a PETSc kernel that stores all the matrices.
Yeah.
And when you so there is a. Is it true that there is also like an instance of PETSc running?
Yeah, I mean it's exactly like FFglut. So there is a so I don't know the name of the process, but just basically PETSc is starting a process just for the visualization purpose, and it's running until you kill the window. And just as FFglut, for example, you can zoom in on the values and so on. But just like FFglut, it's terribly ugly. But for educational purposes, it's not that bad. But yeah, it's yeah. Don't ask me too much. I know very little about this part of PETSc, but the idea is like FFglut. Okay. So maybe this morning I mentioned the fact that maybe you want to post-process your matrices in MATLAB. And so one of the nice things about PETSc is that the viewer format is quite flexible. And so, for example, instead of MATViewDraw, you can have the matrix being printed to screen using the ASCII format. Okay, so for now, I will just remove the visualization. So tac, okay, so it's quite huge. So you can, for example, use a file, so mymat.txt. Okay, now I can look at my maths and I have the matrix. And maybe you don't want to bother understanding and deciphering what is the PETSc format. And so maybe you want to stick to something which is much simpler, like the MATLAB format. And so you can do ASCII MATLAB. And so instead of mymat.txt, I will just use mymat.m. Okay, and so if I look at my mat, then I have something which is hopefully understandable by MATLAB. Okay. Any other question?
Yes, well, how the linear system is solved.
Okay. So this is the next part. I have, I think, 30 minutes for the Lagrange multiplier. So now we go into the details of the linear system. So yeah, for now it's just at -1. So we know very little about the linear solver. And so by default, I don't think anything is set up if you don't do anything else. So I will just check tac KSP view. Okay. So you have seen again the underscore view. And so it's the same. Again, we follow the PETSc lingo, the PETSc options. The idea, once again, is that if you are doing some development in FreeFEM, and then you want to try something else, I don't know, you want to solve the same linear system in your commercial software, which is also using PETSc, maybe you want to be able just to copy paste your string of options and not have to change all the parameters and pass different arguments and whatnot. And so we parse by default everything that is passed on the command line to PETSc. And so whenever there is a dash, whenever there is an underscore view, it means that we want to see on the screen or in a file some information. And so here I have the dash KSP underscore view to tell to PETSc that I want to display some information about the linear solvers. So remember that KSP is Krylov subspace solver. So here we can see what are the default parameters for PETSc. And you may be a little bit surprised by the default parameter, let's say, which are quite basic and not always very efficient, but anyway, it's how it is. The default solver is a block Jacobi method. So we basically invert local matrices corresponding to each local block, each local diagonal block. And instead of performing a full inverse, we perform an incomplete LU factorization with 0 levels of fill. So it's a quite inefficient preconditioner, but it's the default in PETSc. But again, you can leverage the flexibility of PETSc. And so, for example, if you want to solve exactly the same problem, but with an LU factorization, which is, of course, much more robust, but much more costly, you can do PC type LU. And so here, you can see that I'm using an exact factorization. So you can set those parameters up in the command line. You can also set them up, directly inside the script. And so, for example, you can do set a s params equal PC type LU. You can do also many fancy stuff like KSP view final residual to compute the final residual of the linear system. And you can do, for example, fancy stuff like algebraic multigrid, so GMG, KSP, you can change the side of the preconditioner, PC side right, and then you can do KSP converge reason to show what is the reason for the convergence of the iterative solvers. What's also interesting is that when you are mixing linear systems, so for example, one system for fluid, one system for structure in an FSI simulation, you can use prefix. And so, for example, you can use prefix equal something like first system. And so then we have to do first system PC type LU, first system TAC, oops, sorry. And then the same for the second system, prefix. Oops. And then instead of first system, we do second system. You see also push prefix. Yes, oh, good idea. Something which is more pleasing on the eyes is to play around with prefix push second system, and then prefix pop. So you can push as many prefixes as you want, and then you need to pop as many prefixes as you pushed. So here it's not very important, but when you have nested solver, then you can, for example, push one prefix, then set some options, then push some sub prefix to specify some sub options, and so on and so forth. So it's very powerful. Yes.
I was wondering also, so inside the keyboard, are you passing these arguments to PETSc, or are you converting each of these arguments to PETSc or to C++ PETSc object?
No, it's directly passed to PETSc, and I can actually give you the reference to the precise function. It's something like PETSc options insert string, I think. Yep. Yeah. So there is no fancy machinery. Whatever is inside S params here is put as is as a const char of PETSc option insert string.
So if you use the function set, it will assign it the matrix you are passing.
Yes.
Well, if you call it in the argument, it passes.
No, that's the small. I mean, that's the one issue. Let's say. I mean, that's one issue. Is that in this API you can see that there is no notion of the matrix. So for example, in fact, I think, so first it's that. Here I'm using a prefix. So the prefix is tightly linked with the mat that you pass. But here I could do something like tag. I mean, if you don't specify the prefix, the name. Yes, exactly. Because here there is no link, there is no reference with the mat. So in fact, I think we can do something which is quite counterintuitive, but we could do, I believe, something like set the prefix in the first line and then set the strings parameter, but on the other matrix. I probably this will work. I don't know. If it does not work, maybe there is something that I need to fix. Anyway, so I'm always confused whether the underscore must be put or the dash must be put. So maybe I will have some warnings, but anyway, let's have a look. Tac. Second see. Wait, so I want to remove the verbosity because it's painful on the eyes. Okay, so for some reason, what I just said is not working. Why is it not working? So maybe I have some safeguards under the hood to make sure that I'm using the S-parents for the proper matrix. I'm surprised. I'll need to double check. Not sure why it doesn't work with A as input, but need to double check. Anyway, we see that with an LU factorization, we get a very low error, a very low residual, and we see that with our multi-grid solver, we converge in 10 iterations. It's Poisson problem, it's not very difficult, and that's nice. Other question, maybe? No?
Maybe you can just report on how we reset the preconditionals, the S-parents.
How? Mm-hmm. Do you know how to do it? Yeah, okay, so that's one way to do it. So you can do PC type none, which will reset everything. So to this day, there is no So to this day, I don't think there is a trivial way to reset everything. So for example, if I do options view, I think, we can still see that, for example, the PC side is set, the converge reason is set. So maybe this is something I need to add, an easy way to remove all options that have been set. So something like set B, reset equal 1, which will basically remove all options associated to the B from the option database. But yeah, currently, if you want to just rebuild the preconditioner, you go from PC type none, and then you redo something like PC type hyper. Tac, ça sert à rien. Ça sert à rien. And so now if you resolve the problem, it works just as well. So Hyper is another multi-grid solver. Okay, so we jump to the problem with Lagrange multiplier, and so what we want now is to basically solve a linear system where we have no Dirichlet boundary condition. And so I think there is an example. So I will try to mimic what is done in sequential. Tac example. I think it's inside Laplace Lagrange multi. So in this example, we solve a block system. Okay, and so we have a matrix A where there is no Dirichlet boundary condition. So it's a pure Neumann problem. And so we impose a constraint in B as I think it's the mean pressure. Where is B? The mean pressure must be equal to 0.
Do you have another example to, instead of impose the mean pressure, do you have a kind of extract a surface mesh by Lagrange multiplier? For the
so we could try to just impose the mean pressure on the boundary.
In that case, the mesh, there's no separate mesh.
So so if we do mesh,
Extract the mesh out.
extract, yes, I think the extract from to extract a mesh shell, we need. I'm not sure extract works on a 2D mesh. No, wait, it should. Just give me one sec. Mesh L, no, mesh L. So I'm very rusty with that API. So tac. And so int labels equal and so the error that we get, I'm guessing, is that just extract it correct. Yeah, I'm not sure we can extract.
I tried before.
Okay. Sorry, we can in fact extract, but it's a mesh L. And so tac, what is? Okay. So if we run this in parallel, and so what do you want to do with this?
Define the Lagrange multiplier on this mesh, on this boundary mesh, and to enforce the Dirichlet boundary condition.
But why you would want to do that? Because here you have the mesh, and so you can just define varef v Lagrange uv, which is int 1D on the boundary of th.
No, I mean Lagrange is a unknown, is a variable to solve Lagrange multiplier. solve together with the U and V. All right.
So just I will do one thing, and maybe after you can ask me how to change things. Okay. So what I want here is just to impose the mean value of u on the boundary to 0. So again, I can do this v. Okay. And so now I can define, so I can just do as in the sequential code. And so I can assemble my constraint. So it's called B here. Okay. Oops, sorry. And so I've called it V Lagrange 0. And so, okay, so I've mixed up all the systems. So it's a little bit difficult. I don't really care about this part. Okay, and so now I need to define a block matrix with both A and the Lagrange multiplier. Yeah. And so I need to, so I can follow the usual notation. So I will call this nest. And so as the upper left block, I have my FEM discretization. It was called, I think, A. Then I have my Lagrange multiplier. And then I have the transpose of my Lagrange multiplier. And I have 0 on the as the 1-1 block. Okay, so here I only have a single unknown, so a single extra row. When you add a single extra row, it's by default assigned to the first process. So all the other process will have a solution vector and right-hand side with as many local rows as A, except the first process, which will have an extra row for storing the value of the Lagrange multiplier. So here, it's a little bit technical, but basically, I need to resize my RHS only if I'm in the process 0. If MPI rank equals 0, RHS.resize RHS.n plus 1. And so I set the last value to 0, RHS.n minus 1 equals 0. And so the solution vector, where is it? It's called sol here. I will define a temporary array, real int temp sol, which is the size of sol on all process except the first one, so MPI rank equal 0, which will be of size solution n plus 1. Again, the extra coefficient is just to handle the last value of the nest matrix. So the last coefficient is used to store the value of the Lagrange multiplier. Okay, and so now I should be able to do TMP sol equal nest minus 1 times RHS. And if I want to plot, I just need to do sol. Okay, so plot the sol parallel solution to the Poisson problem with a constraint on the boundary of TH. So sol will be equal to temp sol temp. So again, here it's a little bit of bookkeeping because I need to remove the last coefficient of the associated to the Lagrange multiplier. I don't care about the last value. And so need to remove the extra last row associated to the Lagrange multiplier, but only on process 0. So TMP sol is equal to TMP 0 up to TMP sol dot n minus 1, otherwise TMP sol dot n. Sorry. Yeah, I'm actually not sure of what I'm doing here, so maybe there will be errors. RHS before line 97, 97, okay, missing semicolon, easy to fix. So, up. So we got an error. Submatrix dimension are incompatible with nest block, okay? So what PETSc is telling us is that we are trying to assemble a block matrix here with non-matching dimensions, okay? And now I see the error indeed. So we have an error because the matrix A is a PETSc matrix and B is a FreeFEM operator. And so we are missing the link between the local finite element spaces and the distributed matrix, which is which has no overlap. And so we need to convert our matrix, our vector in FreeFEM numbering into a vector in PETSc numbering such that the dimensions are matching. So what we see here, the higher value, this is the quantity which is defined on an overlapping mesh, but we want a value which is defined with no duplicated unknowns. So the higher here is the greater value, so there is overlap, and here is the lower value, so there is no overlap. And so again, there is a small utility routine which can be used to switch between the numbering between FreeFEM and the numbering between PETSc. And so the small utility routine is called change numbering. And so I will need to define a new vector. So B, no overlap. And so we need to change the numbering according to the distributed FE space, which is stored in the mat A. And so first we have the FreeFEM vector, and then we have the PETSc vector. Okay, and so now there should be no dimension mismatch, I think, hopefully. Okay, no dimension mismatch. The solution does not. It's alpha equal. Yeah, okay. I think it's alpha equal 10 to the power of 30. No, 10 to the power of 10, sorry. Just for good measure, I want to use NLU factorization. It's already, no. And so block. Wait, it's not. Wrong operator. So this is just for my to-do list for this evening. Double check. So the norm is good. And now if we look at the KSP view of the second system, I think I called it block, sorry. So block KSP view. We can see indeed that we have a nested matrix with first the upper left block, which is a sparse matrix of type Aij. We have a dense Lagrange multiplier on the first column, second column, first row. Then we have the transpose on the second row, first column, and then we have a 0 as a Lagrange multiplier, as the diagonal for the Lagrange multiplier. And we are solving the system using an LU factorization using MEMS.
But now if you think about that, instead of enforce the mean value to be 0, you enforce every single value continuously. I wanted to the Lagrand like go inside the integral. The Lagrand like go inside of the integral. So you have to define a surface mesh, which the Lagrand sits on the surface mesh.
Okay.
So you agree? So in this case, you have to define.
But okay, we agree that this is the Lagrange multiplier.
But but in this case, it's a scale, just a number.
Here.
But I mean, because you enforce the integral,
Yes.
the u is 0.
Yes.
But instead of doing that, I mean, you instead not the integral of u, you put your Lagrange multiplier inside the integral. And
I'm not sure I understand.
we can talk about it afterwards.
But anyway, so here I chose the easy route, let's say, of defining everything on the same mesh. Okay, if I understand correctly, no matter how you want to define your Lagrange multiplier, one of the difficulty in what you were mentioning previously is to work on a different mesh.
No, let's say instead you want to enforce u is 0. You enforce u is the specified function using Lagrange multiplier. How are you going to do that? You need a distributed Lagrange multiplier to inside the integral. In which case the Lagrange multiplier is like a variable defined on the surface mesh instead of just a scalar.
Yes.
So in that case, you have to extract a mesh, define a variable, and deal with it.
Yeah. So again, if the difficulty is stemming from the fact that you are dealing with a sub-mesh or an extracted mesh or a different mesh, so I will give you, unfortunately, the same answer as this morning. The big difficulty is just finding the proper correspondence. So just as we did here, where we have the correspondence between the local FE space and the global FE space, we need exactly the same when you are dealing with a submesh. And so, for example, there is a tool which is quite useful. I will show next, which is a way to get the reference the numbering of the elements in the initial global mesh. Okay, and so for example, this can be used. This can be retrieved using another macro, which is THN2O, I think. New. Okay, and so this will be an array to store the the permutation from the the reindexing from the global mesh to the local mesh. Okay, and so for this to, if I want to show you what it can be used for, I need to back up my initial mesh, and so I will do th backup. Okay, I need to make sure that both macros are working together. I'm not sure, in fact. Sorry. So it's an array of integer. My new to old. What is? I need to specify a size, apparently. No. What is the issue? 149. Something else. My new to. Sorry. Okay, better. And so the name of the game when you think about distributed computing is always to find the proper correspondence between some distributed quantity and some other distributed quantity. So if you have an extracted mesh, depending on how you do the extraction, the link between the surface mesh and the global mesh is trivial, or it's not at all. Okay, and so here, for example, I will show you how to get the proper reindexing from the local subdomain to the global mesh. But it will depend on your application and how the mesh have been built and how they are connected one with the other. So with my new to old, you can use a keyword in FreeFEM which is called restrict, which again gives you a renumbering of the degrees of freedom. So first, I will need to define a VH on the global matrix, VH global, VH backup. It's defined on TH backup. And so I will use the same FE space. So the FE space is VH. And then I can do int restrict equal, no, I will call this restrict. And so again, I'm always getting the order wrong, but it should be something like VH backup, and then my new to old. So does that run? No. Of course. It's not VH here, it's the type of finite element we used. And so for VH, it was PK, I think. Yes, PK. Okay, this runs to completion, so I think I didn't make any mistake. And so now you can do something like VH backup, sol backup. So you can do something like sol backup, tag of rest is equal to sol. And if I plot sol backup, just on the first process, I have my restriction of my global solution just on the subpart of the global mesh associated to the first subdomain. Okay, and so you can extend this. So again, this is one way to get the correspondence between one part of a part of a mesh and the subdomain and the MPI process. And so when you can do the same with a subpart of the mesh or an extraction of the mesh. But yeah, the name of the game again is to just find the proper indexing and make sure that you have a correspondence between one finite element space and the other. Once you have the correspondence, you can mix operators, you can assemble block matrices, you can do whatever you want. but you need to be able to track how, for example, the extract mesh is built depending on the global mesh and so on.
I remember you have an example of a sequential code to say using a multiplier to enforce a non-homogeneous deletion, non-zero deletion running condition. And can you simply do that? Say you want to enforce your to be x or x times 1.
What is the example?
There is an example.
Do you remember the name of the?
Yeah, it's a sequential code. But in your code, can you simply modify the code to use a Lagrange multiplier to enforce a non-zero one condition?
How so?
Not a number, not 10, not but say x.
Yeah, I don't see why we couldn't, but as long as you can write this down using variational formulation,
That's then you will see the problem. You can't do that using one scalar. You can't do that using a scalar lambda.
okay. So you need to use like a new FE space
Yeah, you need
on the boundary.
Yeah.
Okay, as long again as you know the correspondence between the numbering of the FE space on the boundary and the global FE space, you can do that. So for example, again, so Pierre mentioned the example earlier today. There is also an example, there are many examples that does this thing like coupling a volume with a surface. And so as long as you can extract the mesh according to some rules such that you know the numbering of the extracted mesh according to the initial volume mesh, you're perfectly fine. You can mix things together. Oui.
It's not completely clear for me. So you say that in the PETSc numbering, there's no overlap. While in FreeFEM there is.
Yes.
So what's going on there? I'm not sure to understand why. So why do we start with overlapping meshes and then suddenly there is no overlapping in PETSc?
Okay. So again, that's one way to do the finite element analysis in parallel. So if we think, for example, of an unknown, so we have the top subdomain, okay, which is going down here. So we have these two mesh of elements of overlap, okay. And so if you think of the finite element method, and if you do, for example, the assembly on the point where my mouse is, you know by the definition of the finite element assembly that you need to integrate the basis function on the on all the elements touching the node. Okay, and so without overlap, we would need each process to communicate one with each other, such that we sum up the contribution for nodes that are not local to the process, but that are touching the node, but that are on other processes. Okay, so that's one way to do. That's one way to do parallel finite element in parallel. Okay, you have basically process 0 here, which does all the integration there, and you have process 1 here, and you have basically both processes summing up the values in here. Okay, and so this requires communication, this requires summation, and so on. So here we use another approach, which is based on what is often called in the finite element community ghost elements, where basically each process has an extra layer of elements. So for example, process 0 will be in charge of, will have access to all those elements, such that when he wants to assemble the values associated to those nodes, he has all the triangles or tetrahedron touching the nodes. And so he's perfectly fine doing the assembly fully locally and just with no communication. Of course, when you do this, you have the same for process 1. And so you realize that the unknowns associated, for example, the unknowns here and there are on both processes. When we solve Ax equal B, we don't need to duplicate the unknowns on both processes. And so that's why I mentioned that PETSc has no overlap in the sense that first we have in FreeFEM the ghost elements, and then when we do the mat create, we basically create a filter such that the overlapping domains can fit inside a matrix with no overlap. So we basically trim the unknowns which are owned by another process, or we keep unknowns that are owned by ourselves. And this is how we go from a duplicated unknowns with ghost elements to a matrix X equal B, which is exactly equivalent to if we were assembling in sequential with no ghost elements, with no duplicated unknowns. So that's why the PETSc objects are without overlap and the FreeFEM objects are with overlap. And so we can actually check this in the FreeFEM's code. If we do something like cout vh.endoff versus a.n, we should get vh endoff with overlap, so greater than the number of local PETSc unknowns. And so if I run this v0, maybe with slightly more processes, the order is confirmed. This is with the overlapping unknowns, the ghost elements. But at the end, when we offload everything to PETSc, we need to solve X equal B without the ghost element, without the duplicated unknowns. And so we filter some local unknowns to make sure that the system is consistent. Okay? And so yeah, so there is no way to go from one numbering to the other, so PETSc numbering to FreeFEM numbering for matrices. But if you want to change the numbering of a vector, for example, you can use the change numbering that I mentioned earlier. And so you can also go, so this is for going from FreeFEM to PETSc. And then we can also do the other way around, I think with the inverse, or something like that, from PETSc to FreeFEM. Just let me check. Yeah, I mean, there is nothing to see, but is it more clear or
yeah.
It's okay?
Yeah, maybe. And how does it fit in the framework of the overlap Schwarz?
Okay, so yeah, this is the nice thing again about overlapping Schwarz method is that they inherently fit within the framework of finite element with ghost elements. And so for the finite element frameworks, for example, that deal with non-overlapping domain decomposition, so with the summation in the middle and so on, they are mostly suited to non-overlapping domain decomposition method like FETI or balancing domain decomposition method. And so this is exactly the kind of operators that we need in domain decomposition method. So this is why everything is working quite well.
When we use this approach here, it's not the overlap Schwarz decomposition method because we have trimmed the parts. Just we saw the linear system in parallel, but
yeah. So you have to keep in mind that there are two steps: the assembly and the linear system solving. And so the assembly, we do it with ghost elements, but we are not forced to use overlapping Schwarz method for the solving phase. Okay, and so we could say that for the assembly we do overlapping Schwarz, but it does not really make sense because overlapping Schwarz is just a preconditioner, and so there is very a separation of concerns. we do the assembly with ghost elements because it's much easier to do the assembly in parallel. But for the resolution, overlapping Schwarz method fits well within the framework of ghost elements and so on, but we can use something else like LU or Jolivet or multigrid and so on. It's quite technical, and a lot of people mistakenly are confused with the fact that when you do distributed finite element method, you are in a framework that looks like overlapping Schwarz method or Schwarz method in general, but there is it's a separation of concerns. There is one part which is the finite element assembly in parallel and how you do it with ghost elements or with no ghost element, but at summation at each point on the interface. And then there is the resolution of the linear systems. And so there you can use overlapping Schwarz or whatnot, but I try to decouple things because here it's not very a course on preconditioner or overlapping Schwarz. It's just how to do finite element analysis in parallel. Then we can focus on overlapping Schwarz for the preconditioner part, but it's I try to not mix things too much. So actually, there is a question on the chat before I hand it over to Pierre for the part on BEM. So the question is, I encountered a build intersection in what example? So as Frédéric mentioned this morning, the parallel FreeFEM has been around for about 2000. Has been around since about 2014, something like that. And so unfortunately or fortunately, we've made a couple of changes throughout the years. And so in some part of the web, in some part of the repo, there are some old API calls. And so in fact, the build THS stuff like that is part of a very old API where domain decomposition preconditioner were quite intricate with the discretization part. And so I try to split both concerns again. But anyway, I will try to give you an explanation. So the parameter S is used for the refinement of the mesh. So I think we can still use it we can use it now with the new API. So I will comment this out. And with the new API, I think I will need to comment this out. I think it's something like macro. I think now the name is refinement factor. And so I can put, for example, 2. Concurrent, local, concurrent, uniform, refinement factor. Mesh refinement. So let me try this. Non, ça ne marche pas for the reason, I think I need to comment this out as well. Okay, so here I'm doing the mesh refinement in a fully distributed fashion, but it's purely uniform. So there is no uniform mesh refinement, but it can be useful to generate very large mesh starting from a initial, let's say, coarse mesh. Then the intersection and the D are basically parameters related to the domain decomposition and how the local finite element spaces are connected one with each other. So basically, those parameters, those arguments are now completely hidden to the user. And instead of using the build macro, you are strongly advised to move on to the new API like mat create, dmesh create. And if you have issues in the process of transitioning, please let me know and I'll be happy to help you out. I hope you are still online and I hope this answers your question. Any other question?